Hi class, this is Sir Alex Basco and welcome to our lesson in Physics 1. Today we'll be discussing lesson 3.3 and it's still about kinematics of translation, but this time we'll be focusing on free fall. So the end of the lesson for today is for us to be able to solve unknown quantities involving free falling motion, as well as be able to solve problems involving one-dimensional motion with constant acceleration in contexts such as but not limited to the tailgating phenomenon, pursuit, rocket launch, and free fall problems. So in other words, we're going to be dealing with a lot of free fall problems today. But before we start, let's remind ourselves of the equations that we previously got and derived from lessons 3.1 and 3.2. So they're all kinematics of translations equations. One is in velocity. Velocity is basically the distance or the displacement traveled over time. Moreover, we can measure distance by basically multiplying velocity by time, but also using this equation wherein the displacement along x-axis is equals to the initial velocity multiplied by time plus 1/2 of the acceleration multiplied by the square root of time. If you guys remember this, we got this equation from lesson 3.2. So if you guys want to remind how we got that equation, just go back to lesson 3.2. But we usually use this in when we have uniformly accelerating object. We also have acceleration equation wherein acceleration is basically the difference between your final velocity and your initial velocity divided by time. One thing, so these are the equations that we've discussed and derived from lessons 3.1 and 3.2. But another equation that we will get today or derive is this equation right here, where we can use this to actually measure or find acceleration if we have the displacement, the initial and the final velocity. We can also get use this to measuring displacement. Just arranging the equation. Okay, so let's try and derive this equation right here. This last equation. So we know that displacement is basically velocity multiplied by time, and that the average velocity is basically when you have to average. In this case, we have the initial average and the final average. By adding those two velocities together, not final average, final velocity, when we have initial velocity and final velocity, we have two velocities. Multiply those two velocities together, divided by 2, we'll get the average velocity. Moreover, we know that acceleration is equals to the initial velocity minus or the final velocity minus the initial velocity divided by time. By mixing this equation, we can actually find an equation that we can use if we want to find acceleration. So how are we going to do that? So first we'll start with the equation that we already know, where we actually derive previously. Let me just change into a pen. So we'll start with dx is equals to vt. And if we substitute v to average velocity, we'll get dx is equals to initial velocity plus the or final velocity plus the initial velocity divided by 2 multiplied by time, right? So now what we're going to do is we will substitute the value of t but using acceleration. What we're going to do is we're going to rearrange this equation, basically multiplying both sides by time and then dividing both sides by acceleration. From there, we get that time is basically equal to the final velocity minus the initial velocity divided by acceleration. And we're going to substitute t from this equation right here. We'll get that the final velocity plus the initial velocity divided by 2 multiplied by initial or final velocity minus the initial velocity divided by acceleration. And we'll get that 2a multiplied by displacement is equals to the initial velocity plus, or the final, I keep saying initial, the final velocity plus the initial velocity multiplied by vf minus initial velocity. From here, you'd actually get, if you guys know your polynomials, you'll get this equation 2a, just erase this, 2a dx, or 2 times acceleration times displacement, is equals to the square root of vf minus the square of initial velocity. So that's how we derive this equation, and we can use this equation if we want to find displacement, acceleration, or your initial or your final velocity. So that's the equation right there. Okay, so let's try and use this equation in a problem. So let's have a sample here. Sample problem 3.3.1. A car has uniformly accelerated from rest to a speed of 25 meters per second after traveling 75 meters. So what is the acceleration? Okay, so the question here is acceleration. But first, before we answer that, let's write our given. So here we have a car that uniformly accelerated from rest to a speed of 25 meters per second after traveling 75 meters. In this scenario, we would know that our initial velocity is basically zero because it starts from rest. Rest is our initial velocity, which is basically 0 meters per second. And then it accelerated from rest to a speed of 25 meters per second. That means that our final velocity is equals to 25 meters per second. And the time it took for the car to change its velocity from 0 to 25 is 7, or it doesn't have the time, but the distance traveled, or the distance it took for the car to change its velocity from 0 to 25 is basically 75 meters. So that's our dx. And the question it's asking us is basically what is the acceleration. And from the problem itself, we know that the acceleration is uniform, so meaning the acceleration did not change. So the formula that we are going to use here, we see that we have initial velocity, we have final velocity, and we have displacement. So the equation from the equations that we have derived that we can use to solve for acceleration is 2a dx is equals to final velocity squared minus the initial velocity squared. Okay, let's just plug in the numbers and solve for the equation. But first, what we're gonna do is basically rearrange our equation to solve for a, and we get this by dividing both sides by 2 dx. So divide both sides by 2 dx, and we'll get that the acceleration is final velocity squared minus the initial velocity squared divided by 2 dx, and that would give us 25 meters per second squared minus 0 squared divided by 2 multiplied by 75 meters. And the acceleration is 4.2 meters per second squared. So that's how we use the equation. You can also solve for dx if they give you the acceleration instead. So you can use this equation when you have a uniform accelerated or uniform acceleration. So the acceleration is not changing. Okay, and this is only for straight line because this is still kinematics of translation. We're not dealing with uh, we're not dealing with different moving in a different what do you call this? For example, in a projectile yet, we are only dealing with a straight line motion. This is still kinematics. Okay, so that is how we use that equation. Now let's talk about free falling. So what is free fall? So we know that everything that goes up must come down, and we know the reason for that. It's because of gravity, because of the magnitude of the, or not the magnitude, because of the massiveness of the Earth. It pulls things towards it. Large things usually have gravity on them, and we are very small compared to the Earth, so we stay on the ground because of the Earth's gravity. And everything that goes above the Earth must eventually come down, of course, unless you exit the pull of gravity of the Earth. But we're mostly focusing on the surface of the Earth where the gravity is able to pull everything that goes up. And we know that without air resistance, all bodies, regardless of size and weight, fall vertically at the same acceleration, at the same location above the surface of the Earth. What do we mean by that? If there is no resistance or air resistance, meaning we remove all air particles and created a vacuum, no matter the size or the shape or the size and the weight of any materials, they fall exactly at the same time. Well, why is that? It's basically because the only force that is pulling these two together is basically gravity. There's nothing else that prevents it from pulling it downwards. And like here, the particles of the Earth actually has a force going up. This is air, and the gravity of the Earth actually pulls them down. So that creates a difference when there are air particles around. But when there's no air particles around or vacuum, the only thing that is pulling those materials is actually just gravity. And we call that pulling. A special term, we call that uh, well, when there is no air resistance and the acceleration that is causing the objects to move down is actually called acceleration due to gravity. And this is constant. This is unchanging. And this acceleration to gravity, we usually denote it with g. And most especially in negative g, because the acceleration to gravity is always a negative sign. That is because acceleration has direction, and the direction of the acceleration is downwards, or the acceleration due to gravity is downwards. So we always use negative sign to denote g, or acceleration due to gravity. Continuing on, acceleration due to gravity actually decreases with increasing altitude. By this equation, we know that if you change in altitude, or increase your altitude, if you're in higher altitude, the gravity actually decreases. But for all intents and purposes of this class, we will assume that the height is negligible. So the same way that we will always assume that air resistance is negligible. Okay, so if air resistance is negligible and the height is negligible, then we'll always have a free falling motion. And the acceleration due to gravity that causes the objects to fall freely is uniformly accelerated. Hence, we can actually assume free falling as a translation, meaning what that means is that we can actually use the equations we've derived previously and apply it on free falling. All the equations that we've used so far, we have derived, are all moving from left to right. They're all going in the positive x direction. But in this scenario, we will be replacing the x with the y because everything is not moving left to right. We are moving downwards. So these are the equations that we've derived. So one is for displacement, but this is along the x-axis. We just have to change the x to the y. In this scenario now, we are moving in the directions of y-axis. This could be negative x and positive x. This time we are going either positive y or negative y. The same way with the equation that we just derived earlier. We just have to change it to dy, and this time this a right here, instead of using acceleration, we'll be using a special acceleration, and it's the acceleration resulted by the pull of gravity, and we'll call that g. So for free falling motion, we'll use all of this equation, and as you can see, it's basically the same equations, only a little change in the displacement because we are focusing on going up and down. So instead of x-axis, we are dealing with y-axis, and instead of acceleration a, we will use uh, g, which is the letter that we denote when we talk about acceleration due to gravity. Moreover, let's talk about continue talking about free falling. Sign conventions that we have to remember when we are talking about free fall. All the distances above the origins are positive axis. So if we draw our Cartesian coordinate system, we know that this is the origin, this is the positive x, and this is the negative y or negative x. And we know that this is positive y and negative y. All the distances, or basically displacement dy, above the origin are all going to be positive. Remember that? All the distances, or the dy below the origin, are all negative. Moreover, not only distances, but the velocity. Velocity is moving upward. Upward velocity is positive. All the velocities moving downward would be negative velocities. So the negative and the positive sign is direction. Like I've said a lot of times, when we are dealing with negative signs, in this scenario, we are talking about the direction. It's not the value of the magnitude that is negative, it's just the direction of the magnitude. Moreover, the acceleration due to gravity, which is g, will always be negative because the acceleration that we'll be talking about will always be going down. So g will always be negative, hence negative 9.8 meter per second squared. Origin is the point of release, so the origin on your Cartesian system will always be the point of release. For example, a rocket going up, or someone or someone releasing a coin from a top of a tower. That release of coin is the origin. Always treat that as your origin. So when you solve for problems, you won't get lost. Another thing that we have to talk about is symmetry. There is very important aspect in free falling called symmetries. First is called the time symmetry. Here, the time to reach the max height or the maximum height from a starting point is equal to the time from the maximum height to the starting point. So let's think about it here. So we have moving up and going down. What time symmetry is basically talking about is that if I release the ball and it move up, right? Let's try this. Let's say it move up, And it took that ball, let's say, 10 seconds to reach the maximum. It takes it 10 seconds to reach the maximum height. The time it will take for that same ball at the same location, that's very important, same ball at the same location, along the same y-axis, from max going down to the origin, where I released the ball, that would still that would still take it 10 seconds. Okay, so that is time symmetry. The time it takes for anything that goes up to the maximum height. In maximum height, meaning it stopped moving where the velocity is zero. So you can see here that's the maximum height. The time it takes for it to go up will be equal to the time for it to take from the to go down from the maximum height to the origin. I hope that is clear. Another thing that I want you guys to remember is speed symmetry. Any displacement above the point of release, the speed of the body during upward trip equals to the speed during the downward trip. So what do we mean by that? Let's just erase this. Okay, let's say I have again a ball. Okay, so let's think of this as 0 meters, and it's this as 0 meters because that's the origin. If I throw a ball, and let's say this is 5 meters, and here this is going up, and when the ball reaches 5 meters after I throw it, let's say that the velocity is um, let's say 3 meters per second. Okay, so what happens then is when it goes down after it reached the maximum height. Okay, so it reached the maximum height. Let's say it reached here, and then it went down again. And then when it reached the same location at 5 meters, when it is going down, the velocity here would still be the same. What do we mean by that? At this point, at this 5 meter point above the origin, then when it goes up, it is 3 meters per second. But after it had reached the maximum height and it starts to go down, when it reached that same point, that 5 meters above the origin, the velocity here would still be equal to 3 meters per second. So that is speed symmetry. So as you can see here, Vf is equals to Vi. So let's say I threw the ball and my Vi is equals to, let's say, 6 meters per second. So let's say that's how fast I released my ball. That's the initial velocity of the ball. By the time it took for that ball to arrive again at the origin, the velocity of that ball at this point, the final velocity, would also be equal to 6 meters per second because they both start now at the origin. So that is what we call speed symmetry. I hope that is clear. I hope these two concepts are clear together because when you start understanding what is happening in free fall, those are the two concepts that are sometimes very useful to understand. So let's try free falling problem. So let's have a sample problem 3.3.2. A boy tosses a coin upward with a velocity of 14.7 meters per second. Find A, the maximum height reached by the coin, B, time of the flight, so meaning the time that the coin was released until it went back to its starting position because it has to come down, and also the velocity when the coin returned to the hand. Suppose the boy failed to catch the coin and the coin goes to the ground. With what velocity will it strike the ground? The boy's hand is 0.49 meters above the ground. Okay, so let's use my whiteboard to solve that. Okay, so here is the same problem. So before I solve this, let's try to understand what is happening. So let's have a starting point. This point right here, let's use this as A, okay? And we know that this is the boy's hand, okay? And the boy tosses a coin upward with a velocity. So the boy tosses a coin going up. And let's use this point right here, this maximum height, as point B. Okay, the boy tosses a coin upward with the initial velocity. So this is the velocity that the coin was released, positive 14.7 meters per second. As you can see, the velocity is positive because the velocity is moving up. Okay, and then find the maximum height, time of flight, velocity, and then suppose the boy or the velocity of the coin as it returns. So, and then afterwards, the coin returned to the boy's hand. So let's use this as C. So it returned to the same point. It returned to the same hand of the boy. And for D, instead of catching it, it went, on the ground. So that's what's happening on this problem. Okay, so I kind of like draw what is happening. Now let's try and solve this. Let's first write our given. What what's our given in this problem? So boy tosses a coin upward with a velocity of 14.7 meters per second. What that means is that the boy, um, the initial velocity gave the coin the initial velocity of positive 14.7 meters per second. Again, it's positive because it's going up, right? So that's all our given. And then what it's asking us, there are four things that it's asking us. First, what is the maximum height? In this case, let's write as dy max, because dy is displacement, it's the distance, but this time it's along the y-axis, but it's the maximum height. So let's write dy max for our maximum. Next is it's asking us for the time of the flight. How long did it take for the coin to reach to be released from the boy's hand, go to the maximum height, and go back to the boy's hand. And in C, it's asking us the velocity when it reaches the boy's hand. So what is the velocity of the coin when it reached the boy's hand? And in D, it's asking us the velocity when it reached the ground because the boy failed to catch the coin. So it instead of going to his hand, it went to his and went to the ground. So that's what it's asking. So what are the formulas that are we going to use? Since this is free falling problem, so we'll have to use the free falling equations that we've gathered earlier, or the ones that I've showed you, because this is still constant acceleration and it's still kinematics of translation. So we'll just have to use the equations that we got. So that's 2a dy is equals to the square root of the final velocity minus the square root of the initial velocity. We'll also use how to solve for the acceleration, this time acceleration due to gravity. So that's g is equals to in final velocity minus initial velocity divided by time. Okay, and the other equation that we have also is basically dy is equals to the initial velocity multiplied by time plus 1/2 gt squared. So those are the formulas that we have. So let's begin solving our problem. Let's begin with A. What is the maximum height that the coin reached after it is released from the boy's hands? So what is the dy max? So in here, so what is the equation that we can use from all our given equation from all our given equation and our given information, what formula could we use to solve for this? So as you can see, the only information that we have is the initial velocity. But wait, we know that when the coin reaches the maximum height, we know that the velocity at the maximum height is 0 meters per second. We know that because when it reached the maximum height, it cannot go up anymore because it stopped moving. Therefore, the velocity on the maximum height is 0. We can treat this as our final velocity. So now we have our initial velocity and we have our final velocity. And we know we have our acceleration because our acceleration is always negative 9.8 meters per second squared. So it's supposed to be g, 2g, because this is acceleration due to gravity. Okay, so what are we going to use? We can use the first equation. So 2 multiplied by g dy on the maximum height is equals to square of the final velocity minus the square of the initial velocity. Since we're solving for dy max, we can just divide both sides by 2g. So the maximum height is basically equal to the final velocity squared minus the initial velocity squared divided by 2g. And that gives us 0 squared. We know again this is 0 because this is maximum height, and in maximum height that velocity is 0 minus 14.7 meters per second squared, and then we just have to divide it by 2 multiplied by negative 9.8 meters per second squared. Using your calculator, you would actually get that the maximum height that the coin reached is actually 11 meters, 11.0 meters. Okay, so now we have our A. So let's solve for our B. For our B, we are looking for the time it took for the time of flight. So it's the time it took for the coin to reach to travel, the time it takes to travel from point A to point B and then point B to point C. We'll start by computing the time it takes for the coin. Time of the coin it takes to travel from point A to B. How are we going to do that? So we can actually use our second equation because we are solving for time. So that's the easiest equation that we can use. So we have a gravity multiplied by the initial velocity minus the final, or the final velocity minus the initial velocity multiplied by time. Rearranging this equation, we'll get that our initial, or the final velocity minus the initial velocity divided by g. And we know our v and we know our vf because this is b is maximum height. So this is only we're only measuring for now the time it takes for the coin from move from the starting point to the maximum height. And we know that the maximum height, the final velocity in the maximum height is 0. So time is equals to 0 minus the initial velocity, which is 14.7 meters per second squared, and then divided by negative 9.8 meters per second squared, because that's our chi. Using your calculator, you would actually find that the time it takes is 1.5 seconds. But wait, this is not our answer yet because we are looking for the time of light. That means we also have to compute for the time it took for the coin to move from B back to C, or basically back to A. C and A is basically the same. This is the hand of the boy. So how are we going to do that? We can do that by understanding there is time symmetry. Remember, the time symmetry states the time it took for a ball to reach its maximum height from origin to the maximum height will it will have the same amount of time it will take when it travels from maximum height down to position. So basically, the time it takes is basically 1.5 times 2, and that gives us 3.0 seconds. So that is our answer for B. Next, let's solve for C. In C, the velocity, what is the velocity when it returns on the hand? And I hope you guys catch it by now. We can actually use speed symmetry. You guys remember what speed symmetry is? So the point this the speed symmetry is that at any given displacement, the speed when it was going down would be the same speed when it goes back down at that exact same time. So for example, let's have this point right here. So the speed of the coin at this point right here would when it goes back down for maximum height, it will have the same